This video contains everything about what's behind this graph and how you can create this graph by yourself step by step using Wolfram Language. I happened to see this very interesting YouTube shorts by Merlino Math about Thomae's function, the rational spikes. So I would like to show you two ways you can play with it inside the Wolfram Language. The first one is quite straightforward. You can go to the demonstrations website and search for the modified Dirichlet function, or use the link below in the description. You can just directly download this demonstration, and you can play with the spikes, the maximum denominator, choose triangle or graphs to visualize the same function. Okay, and if you have the source code downloaded, the notebook will show you the core function that to generate this demonstration. So I'm going to show you another way that's I think it's with a much shorter code than this, and give you extra information about this particular function. So with the shorter code implementation, let's just expand this section, and we will use a built-in function called the Farey sequence. I'm quite surprised that if you go back to the Wikipedia's page for this Thomae's function, there's nowhere on the page that mention the Farey sequence, which I think is a very intuitive and straightforward implementation of this type of function, because you can see that fx defined for p over q, which is return 1 over q for the rational number, and p and q are co-prime. This actually fits directly inside this Farey sequence. So let's see how to use the Farey sequence for this implementation. So if you don't quite remember how this function works, you can just type double question mark in front of function, and there will be a short digester box for this function, and you can click web or the information sign here. It will give you the help page for this Farey sequence, and you open the details, and you can check some of the simple examples here, and also there are a bunch of nice extended examples and applications for this function. Okay, so let's go back to this example. Let's see. First, I will show you a simple code snippet for Farey sequence on 20. So you can see this is definitely more than 20 terms, because Farey sequence specify you can find all the fractional numbers from 0 to 1 in the ascending order whose denominator does not surpass 20. Then let's replace 20 with 66. And for visualization, we can safely drop the last point 10 in this sequence. And then we can just visualize this function using the definition of Thomae function. And we grab p, that's all the rational number we have in this list. And we want to just use the denominator of each item. So it is 1 over denominator of p. And this syntax sugar here is denominator is can thread through every element in the list. For example, I want to extract the denominators of everything inside the Farey sequence 20 here. So I can just type denominator. Then we have the denominators of odd element. And in this case, the height is 1 over the denominators. So the other way we can do is just simply wrap 1 over to the outside, and then this rational numbers becomes 1 over some number. Okay, So we do the same thing in this list plot and use transpose so that each P is making a list with the element in the 1 over denominator case. And then we can just run this code, and we have this beautiful generalized dirichlet function, or the Thomae function plot on the graph. It's very interesting. You can play with it and change the number, say 120, and you do the same thing. And at this time, the plot will be really crowded. And most of the new items probably is add around something on the bottom, so you won't see it clearly. So the other way you can handle that is maybe let's try, instead of 1 over, let's try log. So we have a very different plot. Also looks quite cool. So it's because for inverse, the smaller number gives you higher value, but log, the smaller number is keeping small, because log is a monotonic increasing function. So this gives you a different visualization for the same value. And the next question is, what is the number of items in this Farey sequence, or the number of points that's used for this visualization? Here we can use, for example, let's just turn it back into 66. And you can see this number is 1329. Okay, so this is associated with the definition of a Farey sequence. If you go back to the definitions, you can see that it only contains fractions between 0 and 1, and denominator not exceeding n, and all the items in the Farey sequence must have this form. It's P over Q, and the PQ are co-prime. Okay, so you can see this is the value from Farey sequence of 20 items. So what about the 21? Okay, you can see this is the list of 21 items, right? So the question is, how many terms are added between these two lists? So you can do complement use Farey sequence 20 as the second argument. Okay, run this code. You can see everything you added must have denominator equal 21, all right? But not everything with denominator 21. So say you don't have 3 over 21, because 3 and 21 shares factor 3. So it is 1 over 7. So this will not be included. So this is a very good example to show its connection with Euler phi function. (12) 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because they're exactly 12 number that's co-prime with 21. So you can see that from Farey 20 to Farey 21, you add 12 terms, which corresponds to the number that's co-prime to 21. It's the Euler phi 21. When n equal to 66, there are 1329 items in the Farey sequence. And this is exactly the sum of Euler totient function from 1 to 66 plus 1. This guy is basically you have a different convention if you want to throw away the 1 at the end or not. So in our case, we keep the 1 at the end. So in total, we have 1329 items. This number really matches. Okay, so this is sort of the idea behind the crowdedness of this plot if we choose p equal to like 66. And this number actually increase quadratically. And we have a very well-known growth rate for this type of sum. It is the sum of all the Euler phi follows a quadratic increase rate. So it's a 3 times n squared over pi squared. And we can just replace n equal to 10,000 in these cases and to check how close these values are. I can use floor function to extract the integer part of the above result. You can see these two numbers are quite close, around 30.4 million. Thanks for listening. See you next time.